Welcome to the pre-recording of lecture 31, the first half of the 16th session in the middle of the 6th week in the 8-week summer course, Introduction to Computer Science. So the point of today is to introduce the notions of complexity and cost. Um, That's at the conceptual, at the theoretical level. And then we will see several ways to measure the cost of Python programs. In this course, cost of algorithm is equivalent to the timing of a Python program. The distinction between cost and complexity is important because, of course, things are not good when our programs are not very efficient. But for some problems, the problems are so hard that no matter how efficient you are as a programmer, it will still take a really, really long time to solve. So I will start with a cartoon I liked from difficult book and theoretical computer science. So the citation is below. So the caption is about an unfortunate encounter of an employee with a boss. So why can't you get it to run efficiently? Um, this is not what you want to be saying. What you want to be saying is that uh, it cannot be done. So finding an efficient way to do things, there is actually no algorithm possible, no efficient algorithm possible. Um, so if you make statements like this, you better be familiar with the literature and the proper terminology to talk about the difficulty of a problem, the difficulty of a problem, and therefore also a problem is difficult when there is no efficient algorithm for it. So this is an intuitive introduction to algorithms and the cost and the complexity. So an algorithm solves a particular problem. An algorithm has a cost. If the problem has an efficient solution, then your algorithm also should reflect that. So, but if there is no efficient algorithm, you actually want to know um, what is the complexity of the problem. So here is it then. So when we talk about complexity, we are referring to the hardness of a problem, how difficult is a problem, how hard it is to solve the problem. When we talk about costs, we think about the property of the algorithm, of one algorithm to solve a problem. So algorithms cost, problems complexity. It's important not to confuse those two. When we think about efficiency, we think about the use of space, the use of time. Um, so, of course, when the output is extremely large, then also any algorithm that computes the output will also take a time that is proportional to the size of output. Um, so typically we want to have measures that depend on the input. We can think about different inputs. We have a worst case, best case, average case. Think, for example, about sorting. So you may consider sequences that are almost sorted, as opposed to completely random sequences, um, or completely sequences that are sorted. So you have the worst case, best case, average case. So among all the sequences that you can consider of numbers, what is an average case, for example? All right. It's very important for software development that we have an idea about the complexity. So in the software engineering stage, the analysis, I was mainly referring at the time about the analysis as far as the amount of resources that are needed to complete the program. But the analysis should actually also consider the complexity of the problem. So there is a strong correlation. If you are a good programmer, then you will find the best possible algorithm that has a cost that is almost entirely coinciding with the complexity of the problem. Also, if you are studying the quality of algorithms, a cost analysis must be made. So that's a separate, that's also actually an aspect of the testing that we considered in uh, in our previous session in lecture 29. Some applications. So there is public key cryptography. A sequence sequel to this course will study coding and cryptography. So the hardness of certain problems ensures the security of transactions. The cost analysis is also important to the tuning of algorithms. So we have the theoretical applications, but in computer science, all theory is actually can be applied. Okay, how do we measure things? We will consider typically here one-dimensional problems. So we have one number. So think about a number of alg a sequence of numbers. So the n would be the size of numbers, the size of the sequence. Another dimension would indeed be the size of the numbers. But let's consider one-dimensional problem. So the big definition here is the big O. So we say that one function is of the order of another function if there exists a positive constant independent of n such that that other function bounds the first function for sufficiently large n. So this is also asymptotic analysis. For smaller values of numbers, there might be some fluctuations. What's the benefit of this big O? Well, you can actually take very simple functions for what is inside the big O. Several examples we have logarithmic cost. Logarithmic cost is binary search. You are opening a book and you want to search for a particular page. Then you open the book in the middle. If the page number you look for is in the first half, you cut open the middle of the first half and you continue that way. Logarithmic cost is actually almost constant. So a sequence of 1000 numbers, it takes you 10 steps. 1 million numbers, it takes you 20 steps. Linear cost, the cost grows linearly. So the summation of a sequence of numbers is an example. So one property there is that if you are summing a sequence of 1000 numbers, takes you a second, then you can expect that 2000 numbers, it takes you 2 seconds. So the cost grows linearly with the size. So you see already the difference between logarithmic and linear. If you go from 1000 to 1 million with the linear costs, that's a huge step up. Then there are the algorithms that are quasi-linear, so there is the n times log n. That is the cost of the or the complexity of sorting, as we will see. So algorithms that are n log n behave as almost linear. Then there is the quadratic cost. If you are doing linear algebra, you're multiplying a matrix with a vector. You're solving a triangular system. There the cost is quadratic. What this implies that if you double the size of your problem, the running time will be multiplied with a factor of 4. So and then there are the cubic costs. Um, Solving a linear system is a cubic cost. Um, Typically, when we say efficient algorithms or if problems for which efficient algorithms exists, they actually have a complexity which is polynomial. Um, so the n squared is polynomial, n log n, it's not looking like a polynomial, but it is bounded by n squared. So it is bounded by a polynomial cost. Exponential cost, so many interesting problems, they can only be solved when you you accept an exponential cost. Uh, these are the really hard problems. Sorting is extremely important. With this slide, I want to give the intuition for the n log n. Um, what are the kind of inputs you can expect? Well, if you have n numbers, then the number of different input sequences, assuming that all the numbers in the sequence are different from each other, that is n factorial. For 3 numbers, you see here all the possible inputs. So if we want to sort the sequence 1, 2, 3, then we have 6 possible input sequences. And you see the number of comparisons that it takes to distinguish those 6 input sequences is here organized in a tree. And that is independent kind of the algorithm. So in order to separate these 2 sequences here from each other, you must do 3 comparisons. So this is already an indication that for 3, you may need to do 3 comparisons. Sometimes you may be lucky with 2 comparisons. In general, so you can also write down, my slide was not big enough, but you could also write down the 4 factorial. So for 4, you will have 24 leaves in your tree. So your tree is then, it has n factorial leaves, and that is bounded by the number of comparisons. So this is an intrinsic, a very hard limit. So the minimal number of comparisons that any algorithm would need to take. All right, so then there is the property of the Stirling property here that I'm just glancing over, but the n factorial can be is proportional to this n to the power n divided by some constant to the power n, and then also a factor in n. But the big O notation looks at the dominant factors, and this is how you arrive at the n log n. So this is a hand-waving argument, just to state a very important result, that for any algorithm that you consider for sorting numbers, you cannot do any better than n log n. We have a sort in Python, so we will check how good this sort is in Python. Okay, we have different costs, logarithmic polynomial, exponential, three different distinct classes. So we can try to classify any arithmetic problem in one of the complexity classes. So polynomial time is the class of problems for which efficient algorithms exist. The evaluation of a polynomial, so if you use the nested Horner method, this can be done in n multiplications and n additions or subtractions as well. That's clearly a polynomial time algorithm. Then there is the class that's kind of in between, a non-deterministic polynomial time, NP. It means that you can verify a solution to the problem in polynomial time. Root finding is one of them. So you can guess a root and evaluate it at a polynomial. So the evaluation, actually the verification, that goes in polynomial time. The root finding itself may not be polynomial. And actually the class of determining the number of roots to a nonlinear system. And this is also belonging to the class of all volume problems. The estimation of pi actually fits within that class. For which Monte Carlo simulations are determined. So these are actually these sharp p. So even if p equals np, and most people think that p is not equal than np, then actually you would still be left with those very hard, sharp p hard class of counting problems. So this is just one very crude and coarse overview. So there are many other complexity classes there. But for this course, P, NP, and sharp P are the three important classes that you will need to know. Here is another undecidable problem. Can you find a program that, given a program and a finite input, decides whether that program will terminate or not? So this is an undecidable problem. You actually can't find an efficient solution for this problem. So this is just a sample problem. There are many of those very important problems for which no efficient solution exists. All right, we have seen the class counting, counting flops. In scientific notation, we work with scientific computation. We work with floating point operations. And there, the cost analysis is often measured in the number of floating point operations that is performed per second. So flops is also the plural of the word flop, but it also is a speed measure. So we have seen the class flop floats and for operator overloading, and here this is where we could use the class flop floats. So that is one way also to measure the efficiency or the cost of an algorithm. So the cost to evaluate a polynomial, and in more general terms, you could consider the cost to evaluate an expression. Okay, so let's get practical now. The cost of algorithms is here in this course equivalent to the timing of Python programs. Like with testing, we distinguish between static and dynamic. In the static analysis, you look at the source code. So we have seen file processing. You could take any program and have that program count the number of multiplications and the number of arithmetical operations, and do lexical syntactical analysis, and also look for the loops. We will not do this, but in a way you should definitely, as a programmer, be able to recognize if you see nested loops, two of them, one loop inside the other, then that is an indication of a quadratic cost. Three loops nested into each other is an indication of cubic cost. So if you see functions like that, they may be the bottleneck. Um, Also, when data structures are used, composite data structures, then you can look at the size of the memory. Okay, what I will do in the second part of this lecture, after the slide presentation, I will give several methods to um, time in a dynamic way the running of the code. So what we can do is that uh, we can measure time at the command line. Python provides a time module. There is the timeit, there is the OS time, and then there is also the profiling of the code. Um, okay, um, this also actually fits within the testing of the software quality. If you deliver a software program, often a very important quality is its efficiency. And we can test to pass, we can test to fail. For programs that solve important problems, you can time them and pushing the program to the limits of problems that can be solved within a reasonable time. Whenever timing is done, one should actually also list the properties of the computer. So that is something that's also important. All right, here are the cost considerations. How long does it take now to sort a list of n elements? Is that now really n log n if we do this in Python? In the last lecture, in the previous session, we covered exception handling. An exception is an unexpected event that interrupts the normal flow of execution. So it should only be for exceptional events. I will try to demonstrate that if an exception occurs in half of the cases, then actually you're better off with an if else. It's no longer unexpected. We've seen that we can import a module and then call explicitly listing the module name dot the name of the function, or we could also import from a module a function that we need. We can do both. For clarity, the importing of the module and then do name of module dot function might often be preferred. But from efficiency perspective, one of the two is really better, and as we will see, working with files is working with persistent data. So make backups on disk. So do checkpointing if your program runs for a very, very long time. What's the cost of that? Is it really so that if you always write to disk, that then your program becomes really slow? Do we care about shorter code? Why do we care about list comprehensions, for example? Okay, um, I have a Jupyter notebook prepared. Um, so I will start with the command line arguments. So because we will do the timing at the command prompt, the timing to sort numbers. So what you do not want to time is the typing speed of the user, but you still want to have the parameter, the size of the list, so the n in our input dimension. You still want to have that taken into account. So what you want to do, for example, you want to see what happens if you double the size of the lists. Um, in Python, you can get the command line arguments using the sys module. So here, this is a code snippet. You import the sys module and then the argv, that comes it's actually from C, so the C programmer will recognize this. So it's you get then the first command line argument. Actually, the first command line argument is the name of the program at position 0. But at position 1, we have then the argument that you give. So that's here in this case the 1 million. All right, we have to convert from the string to whatever numerical type we want to use as the command line argument. Okay, when we sort numbers, we actually want to distinguish between real time and user time, and also the system time. On Linux systems, there is the time command. It will also work on a Mac. So here this is for 100,000 numbers. On Windows, we have the measure command, and this is what I will demonstrate next. So I will type measure command and then the curly braces open, Python sort rand numpy, and then 1 and 6 zeros. So this will sort random 1 million random numbers. Does it in less than a second, 600 milliseconds, 641 milliseconds. So let me now double, and I have 1 second and 285. So I double the size of the sequence of numbers. These are random numbers, and the time actually also doubles. Or yeah, so it's quite astonishing. So we might think that sorting can be done in linear time. So let me do that again. So let me double. So now I'm expecting 2 seconds, and you see 2 seconds and a little bit more than, so 280. I was expecting 560. Let me do it once more. You see the total number of milliseconds. So here we have the 5 seconds. So what you should record from this would be the last number that is shown each time. And you can make a nice markdown table that lists the for every dimension, that actually lists the total number of milliseconds. After a while, what will most likely also start to matter is the size of the memory. I'm expecting here that there is sufficient memory on my computer to store everything quite efficiently. So, but this makes the point that sorting numbers, that is an extremely important problem, and there is the quicksort algorithm that is most likely applied here. In another course, you will analyze this. There are several sorting algorithms. If you were to come up with your own sorting algorithm, it would most likely have a quadratic cost. And these sorting algorithms are still important for small sequences. But when it comes to sorting millions of numbers, then you want an n log n algorithm. Okay, so what I actually should be doing, or should have done as the result of this outcome here, is that two things. We first report the characteristics of the computer, and then make a table with, in one column, the dimension, and then in the second column, the timed, uh, the times. So I did not do this here. I was in a hurry when I prepared this. but this is important. What I want to do is want to list. So on a Linux computer, you would see the different times, and actually I have a Windows subsystem for Linux. I could also actually demonstrate this, but I will not do this here. I will indicate that if on a Windows computer you want to see the difference between the user and the system time, that you can do this with the OS module. Let me go to the next question. So the next problem. Um, Exception is an unexpected event that disrupts the normal flow of execution. So it should be for exceptional situations. What I will do here, I will run two functions. The functions will generate a sequence of numbers, and the numbers will be essentially um, 0 or 1 for the denominator. So in half of the cases, in about half of the cases, I will actually divide by 0. So in the first test, so you see this here in code cell 2, there will be an if-else statement that counts the number of times the denominator was 0. In all the other cases, you will actually do the division. Not reported, but you can see the number of divisions by 0 that have been prevented by this if-else test. I also import the seed because for both functions I want to have the same sequence of numbers. The important for timing is that we can use the time of the time function of the time module that gives us a floating point number. That is a count that measures the system clock time. The system clock time has started from the beginning of some time period, and we are interested in mainly the difference. So imagine a stopwatch. So you press start, something happens, you press stop, and then you take the difference between the times. So what the time actually, the number that is returned, doesn't really matter. What matters is that the difference. We take the difference for the elapsed time. So we encountered in the last lecture the zero division error. So here you see how the division by 0 is handled in the exception handler. So the exception handler suppresses the erasing of the exception and counts the number of times this happened. So I will do this here for 1,000,000 times. So perhaps I should run this. So let me run everything. So, and you see that there is a difference. So in both cases, the count was the same. With the if-else, that count that detected the division by 0 before it actually happened. So you could also say that the division was started in the try except case. So that's why actually more instructions were executed. And you see that it is about 10% slower here if you have to run your exception handler for half of the time. So in half of the cases, this is no longer an unexpected event, and this is an example of where you should not be using a try except, but instead an if else. Okay, what's next? So what I want to show is the import of modules. So if we are using, if you want to compute the sign of a number, we are applying a mathematical function. We can do this in two ways. We can import the mat module and then call the sine function from that module. This is very clear. There is also numpy and there is scipy. Numpy for numerical computing, scipy for symbolic computing. With the math, you have the Python built-in module, and you probably want to distinguish which sine function that you're using. Um, so the other way imports the function from the math module. Here I can use the timeit. So timeit is a module from Python. So if I do the timeit, so I have the setup. So timeit, I should say, has a timer to time statements. Why is that necessary here? So one statement will actually execute extremely fast and it will probably not show. So a sine function is almost as efficient as um, any elementary arithmetical operation. It's in the order of perhaps not more than a dozen floating point computations here in this case. You could do this with a loop, but then actually you also do the loop counter and you have the overhead of running the counter. So the timer actually takes care of that overhead. So you have a more genuine cost, a better timer here. So here I'm doing this 10 million times, and you can see there is a very substantial difference. So in the previous example, we had 10%. Here we have 20%. So it takes 20% longer if you are doing the mat.sine after importing the mat module. A reason for this could be that every time you do the mat.sine, there is a lookup that happens for where the sine function occurs in the mat module. But the main point of this section is again, how do you time functions? Just a function call. How do you do that? All right, we had system time. So when does the system time get large? Well, working with files, you have numbers that have to go from the random access memory onto the file. So this requires the operating system that has to open a file, has to write the number onto the file, close the file. And then here in this case, we will also reopen the file for a reading. So it is important that all the operations here are actually linear in the size. So this is a linear cost. So we would expect that the amount of time actually increases linearly. This will have a significant system time. So let me illustrate this. So I will run this and actually, oops, in both cases, actually the system time is still on a Windows computer is not reliable. So it should not have been 0. Okay. How to fix this? Well, I can rerun it. So let me try to rerun this. No, not rerun, but let's try to do this for a larger number and see what happens to the total elapsed time. So I should have probably doubled it, but I did this times 10. And actually, in a way, you can already see it. So the it is 3 seconds. So it goes from 0.06, it goes to 3 seconds. So I multiplied by 10. So this was expected to be a linear operation. So I would have expected still less than a second. So 625 milliseconds times 10 is zero point 0.6 seconds. But instead I see 3 seconds. Oh, and now actually we see the system time. So the mistake I made was to take a number that is too small. Okay. Let me redo this then. So I'm going to start this with, and then I'm going to double. So this is the experiment that I should have been doing. All right, 10 million. So that will give me 3 seconds, and then I will double it. In the meantime, I have one section left. Okay, so in the meantime, you see the fluctuations. Now it is half a second. Um, why is that? There is also the Jupyter notebook that is most likely also interfering. It might very well be that the Jupyter notebook is trying to back up things. So therefore, I will for all, so the Jupyter notebook itself has an automatic backup. And you see here by doubling, in any case, by doubling this, I do have the system time that actually doubles. But the total user CPU time is actually rising tenfold. So that is something that is really expensive. So I have to run this now at the command line. So let me do a combination of these two. So I have time, I have this put also in. So here is the uh, measure command. And let me rerun the script now at the command prompt. So here you see the user CPU time is 600 milliseconds. So you can see that the elapsed time should not have been 0, but what was reported here, the total milliseconds, is 1 second and 600. Now, if I run this again, let me again run it. So you see the fluctuations that are on there. So that means that the problem size is actually not yet large enough to uh, give a consistent answer. All right, I hope it is not too confusing. Let me show the, so this is the time to sort. There is also the profiling of code, which I have left here out. So I have to improvise a little bit. So I will add this. So it's on the slides, but I somehow forgot to put it. I still have some time. So the last section is the profiling of the code. And I was thinking that there is a profiler. So there is indeed a profiler. So it's a class for profiling Python code. Here is the, so you can run a statement, and it's actually part of the library. So you can or you can run also a call. I was thinking that I did have something that I had prepared. Um, oh, here it is. List comprehensions. Very good. So let me run it in a Jupyter notebook. So here is the script that I have, but just to illustrate. So this is the last question. Is shorter code now more efficient? Do we care about why do we care so much about list comprehensions? Um, so I will run this program in pieces. So I have two functions. One function will do the append, and the other function, so it will each time append a new number, a new random number at the end of the list, and then sum it. Um, in the main program, I will leave it now, or let me, I have already imported. So I have two functions to take the sum of a list. So here you see how many function calls we do. In the first program, so we always do the append. So that is a point that we do. And what do we do with the second list? For the second list, we have only half that many function calls. So that is, so the function calls that are used are the random and the uniform. I think that doesn't differ that much. 1,000, 1,000. Oh, 10,000, 10,000 in both cases. But here I have the append sitting there. So the timer is actually kind of off. It could very well be that my computer is way too efficient for this, and that when I prepared this, I was essentially um, working on. Here you go. So I add a zero, and now you see that indeed the list comprehension is more efficient. So I have 78 milliseconds for 100,000 numbers. Let me take a million, and a million is probably best shown as this. So if I profile this for a million numbers, then what do I get? So 328 million, and you can see that the append is already starting to take 16 milliseconds. So this is an example of how you can identify the bottlenecks in your program. What are the pieces that cost? So you see here with the list comprehension, instead of the append, I'm working twice as fast. So that is the conclusion. If instead of the append, we work with a list comprehension, our program is at least twice as fast. Imagine we also are doing the sum of the numbers. So we're doing much more than just making the numbers. Okay, I was improvising a little bit, but I think that I hope that you have at least some idea on how to measure the efficiency or the cost of the programs. Um, that there is the overhead of the system calls, the overhead also of using the exception handlers, and the and not knowing list comprehensions will also cost you as a programmer. Okay, I do not want to run over time. I'm running over time now, so I will stop here.